there's two of them here, that the world's not two-dimensional, right? So the three-dimensional equivalent of a ellipse is an ellipsoid. So like an ellipse, if an ellipse, an ellipse has a long axis and a short axis. If there's an ellipsoid, I can't draw three dimensions for shit, so that's an attempt at that. There are three axes. The ellipsoid, they're the 3D equivalents of an ellipse. There would be a long axis, there's a short axis, and there's an intermediate axis.
That's three-dimensional?
That's three-dimensional. Now here I have two examples right here, right? If I look and hold them up to you from this perspective, they look kind of similar in shape, right? They're sort of an elliptical cross-section. This one's broken off at the end, so think of it as half of an ellipsoid. But they're kind of roughly the same shape. This one's probably more elongate, or definitely more elongate than this one in this section. But if I turn them in this direction to you, they definitely look different. This one's skinnier than this one relative to its length. And there's a third direction we can look, I guess it would be that way, which is looking at another direction within the system. You're cutting it in this direction, right? So, I might, but these actually are a different shape, right? That's a common problem we run into in the three-dimensional characterization of flow in a material, is we might want to know something about the shape because it relates to the flow, and I'll get to that in a moment. But let's just do a hypothetical exercise. That's why I brought the ruler along. This is a simple measurement, right? I've done this in the field a gazillion times. I can take this object and estimate its long axis. Now, it's broken off the end here. I don't have a perfect piece. But I'm going to wing it, and I'm going to make up a number here. It should be about right. I'm going to say, oh, okay, it must have been about that long. This is called the fudge factor. Its long axis. That's a scientific term. But I'm going to measure a long axis. I'm going to have object 1, object 2, or pebble 2. I said long axis. I'm going to have an intermediate axis and a short axis. So the long axis of this one is 5.0. That's American units. The intermediate axis will be about here, and that is about 2.6. I might have to have somebody help me with a calculator here. I suppose I could use my phone. And the short axis, about 0.7. Now this one's going to be a little different, right? This one's, I'm going to have to wing it here. I'm going to say it's twice as long as this dimension, which is 3.5. So this one's going to be 7.0 long.
Mm-hmm.
Its intermediate axis is about 2.2. The short axis is about 1.2.
So is that 175% and 360% strain?
Well, we'll get to that. Keep in mind that it's different in different sections. These numbers, how am I going to characterize this? The way it's dealt with is ratios. Is the way we ratios is how we deal with the object shape. And there's a common terminology that's used in structural geology that this is the x-axis of strain, this is the y-axis of strain, and that's the z-axis. only referencing to the strain ellipsoid, long, intermediate, short. You got 3 mutually perpendicular axes. Now, what I don't know from any of these is what the original dimensions were, right? I can't know that because I wasn't there when the rock was deposited as a cobble on the seafloor. So, what can I do? I can calculate ellipticities of each of the sections that I cut it in. It's like taking an XY plot, Z plot, right? I can cut it. I can take an XZ section, I can take an XY section, and I can take a YZ section. So I can calculate ratios, which I didn't give myself much room for here. So I'm going to go the other way. I want me to take, actually no, I got plenty of room. What am I doing? I want to, let's calculate X over Z. That's the maximum ellipticity, right?
Like 7.
Because that's long over short. I can also calculate X over Y, which is long over intermediate. And I can also calculate Y over Z, which is intermediate over short. Now, why am I always doing them in that order? This has to be a greater than 1 number, right? It's the ellipticity, long over short for each ellipse. So there's 3 of these. So somebody's got a calculator. Somebody calculate what's 5 over 0.7. That's
7.1.
What is it?
7.14.
7.14. What is 5 over 2.5? That's about 2, right?
1.9.
1.9?
Roughly.
Are you like a good at doing arithmetic? You get it? Good. No. This one's what? What's this one's going to be about?
3.75. What is it?
We got a calculator. Is that about right?
3.7. Fucking A.
Is that right? That does sound about right. Okay, let's do these now. This one's going to be about 5 something. 7 divided by 1.7. What's that? 5.8? And what is X over Y? So 7 divided by 2.2 is
3
something.
Like 3.2.
3.2. And Y over Z is about, what is it, about 2?
1.8.
1.8.
Yeah.
Okay. So let's just kind of look at the numbers, right? That's the maximum ellipticity. So if you cut something in that direction for both of these objects, that would be this view I held up to you. Forgot which was which. This must be, which did I do first? I did this one first, right? This is object 1. Should be actually, yeah, that's right. This should be object 1. So that it's very elliptical on that section. This one's not much. That fits, right? And it also fits when you start rotating this around and thinking about it, orientation. Well, actually, another way to look at it is think about this way. Let's take the YZ section. That's intermediate over short. That's that dimension for object 1, and that dimension for object 2. This one's bigger than that, right? You can see that. Or conversely, I can look at long over intermediate, that's that view versus that view. This one's actually more elongate than that one. And sure enough, it fits that relationship. Fair enough. This turns out to be the key for recognizing that relationship is how we actually use the 3-dimensional shapes, or we characterize the 3-dimensional object or the 3-dimensional strain within a material. In fact, what we do is make a plot called where'd it go? Here it is. Make an XY plot that plots the ratio of over z divided by y over z. Did I actually go over this? Let's see. Well, those are just raw lengths, but I know what I forgot to say. I skipped a step here. It's rather important. If you take a
Is this to find L1 and L from the previous equation you had up to calculate the strain? I'm just trying to figure out where
that's
this.
what I'm headed for.
Yeah, okay.
I forgot an important thing that I might tell you. That if this starts with unit radius, and this has length A, and that has length B, A over B, this is stretch of A, that's the stretch B, such that this ratio, A over B, for ellipticity, why is that? If they have unit length, stretch is final length over initial length. So if the initial length is 1, final length, stretch, is SA, and the short one is that. So this ratio, the ellipticity, is a direct measure of the ratio between the stretches in those two axes of the ellipse. So x over, that's Sx over Sz also. The maximum stretch over the minimum. I'm sorry, I did that wrong. That's why. I'm sorry. I did that wrong.
Oh, and this is what gives you the two small numbers that you're taking away from the big one.
Right.
Okay. That's what I was confused.
Now, because of that, you might notice that if this is simple arithmetic,
Yes, that'd be
you take
5.6.
x over y times y over z, that equals x over z. For constant volume, these ratios are related to each other. So in other words, I should be able to take those two numbers, multiply them together and get that. Plus or minus our round off error. You can check that with a calculator, but it should be, because we just use the same numbers, right? Now, what's the significance? Well, this plot, now that I got it right, first of all, notice that these numbers, what's zero strain in terms of stretches? Or what's a circle in a plot like this? What's a circle? One. 1 over 1 and 1 over 1. So the origin in this plot is not 0, 0. The origin of this plot is 1, 1.
Okay.
That's a circle. Let's plot our data. So that's 2. I'm going to give myself some room here. Here's my number here. Let's go to 2, 3, 4, 5. I got 7 here, don't I?
7.1.
Oh, actually, no, I don't have to go that high because I'm not doing x over z.
Okay.
But let's plot our data.
You're doing.
Object 1 is this x, y is 1.9. And this is 3.2.
3.2. Right?
I got it backwards.
Yeah.
I got it backwards. This is one. I'm looking at it at the wrong angle. They do this right. 1.9, or actually 3.7, 1.9. That's object 1. Object 2 is this
1.9.
3.8.
3.2.
They plot a different place on this plot. Now, why do they plot it different? Remember, if you look at it, think about qualitatively what they look like. This one's kind of squashed, whereas this one's kind of elongate looking. That's the key to this diagram. Let's do it a different way. Now let's look at this a different way. What are the axes on this plot? If you're on this axis, x over y, long over intermediate axis, are exactly the same. It's a circle. And z is different. Z changes. This is where I forgot my Play-Doh. I was going to make one of these. What is that? Squash something. Squash an object. You have a short axis and a circle. It's a squash sphere. That's called an oblate spheroid. Like the shape of the Earth, flattened on the poles and stretched out on the equator. Take this axis. Might be just the other way around. On this axis, this ratio, the intermediate and short axis are the same, and there's a long axis. That's an object. If you take an object and squash it and stick it on, this is a so-called prolate spheroid. Or the better way of remembering it, these are pancakes. And these are cigars. They're circular in cross section, drawn out, or they are, pour pancake batter on thing. You get Latin in one dimension. Unless you make Mickey Mouse, they're little circles, right? So those are the axes. There is a line that divides those two fields, actually. It's an interesting line. That's a line of unit slope. And a line of unit slope in this plot is one in which x over y equals y over x-axis,
Yeah.
X equals y, right?
Yeah, that's where it plot.
That's an interesting relationship because that can only occur because of these are actually stretches. If you're constant volume, this doesn't work if you're a constant volume, but it doesn't. If you're a constant volume, the only way you can have this relationship is if y equals 1. It doesn't change. That's because this ratio has to change because these are connected to a sphere that has a unit radius initially. Stretch one dimension, you're short in the other direction. If those change at exactly the same ratio, that only can happen if this is y equals 1. Does that make any sense at all? I could go through a little algebra to show that, but the idea is pretty straightforward. What's the significance of that? When y equals 1, this is that, actually we referred to that a minute ago. That's a special case called plane strain. What was the scenario we just talked about that was a kinematic system that was plane strain? What did I spend most of the first lecture on? Silence out there. Don't be afraid. What do you think? Just what were we talking about? What's that? Shear.
Yeah, turn, shear,
When you're in shear,
rotating.
You're not changing the reference direction. You're just speeding stuff up.
It'll shorten and rotate, but
Short and rotating, but you're not.
long axis
you're not
just gets
changing the
longer.
dimension. So this line, this unit slope line, is a plane strain line. So you might guess an awful lot of materials lie on that, naturally deformed rocks lie on that line, on that plane strain line. Because if we get deforming shear, they should be plane strain. But deviates from that, there's something else funky going on, actually. What that means is, if you just think about that qualitatively, then, that separates the shapes of objects that are deformed by the flow from everything from perfect pancakes to this position. These are flattened objects.
Which directly relates to the angles on the ABCD chart you were showing earlier, where you can correlate the angles.
Correct.
Gotcha.
Whereas these objects are constricted objects. The farther you go this way, the more it's just drawn out and squeezed. The farther you go this way, the more it's just pancake. And in between, the plane strain objects are, I don't have one, I should have brought one, actually, I've got some, are sort of halfway between these in terms of the shape. This one plots there, this one plots here, right? There's still, see how flattened it is in this dimension? Makes sense in that regard, whereas this one's not as flat. Whereas you look at, this thing still has an elongation in this plane, but it's, the ratios between the two are such that this is more flattened, it's not on the plane strain line. Something else happened to it, that it was stretched in this dimension. This dimension has changed as well as all the other dimensions. It's not, it doesn't lie on that line. Whereas this one is more constriction. Fair enough? So it's just it's a way of representing object shape. Now, it turns out to have some significance. We talk about rock fabrics. This will have quite a big significance because just the same way these objects take on a shape, the elements that make up the rock at a hand specimen scale or slightly larger tend to mimic the shapes of the objects. So just like the picture I showed of the shear zone where the crystals flattened out into the flow in the shear zone, that all the objects do that, the crystals do that in three dimensions too. So the shape of the crystals that get drawn out in the material, or we produce a preferred orientation or fabric, reflect the shape of the strain. And what it means is, since these are squashed objects and these are elongate objects, the rock actually tends to mimic that effect. And again, we'll
But we can get the initial orientation based on the crystals themselves, correct? And then extract.
Not necessarily.
No?
If you're in shear zone, you can do it. So you can see the outside, the material from which it's made. So you have the exterior rock, you see it progress into the shear zone, you can do that. But if you're in a pile of rocks that are all homogeneously formed, you don't know, you don't have an external reference. So all you've got is a rock with a bunch of line crystals. What are you going to do with it? That's where the problem lies. And we'll come to that in a moment. But so just a step ahead, and I'll beat this in your brains later. But it gives rise to one of the things is this is that plot, right? You can't read that, but that's long over intermediate, intermediate over short. And these are the fields we just talked about. Here's a qualitative illustration of the shape of taking a cube and extruding it in different directions. You can see the various shapes as you go around this diagram. And this is the plane strain line. The key point of this diagram, of course, is that this is the flattening field, and this is the constriction field. And it gives rise to different classes of rocks that we can just pick up a rock and characterize it. They're called S tectonites, L tectonites, and LS tectonites, such that S tectonites are just squashed. They tend to have a planar element to them. Whereas these rocks are drawn out in one direction, have a linear element to one. And things in between have both. And those are manifest in rocks when we look at them and we talk about strain. So that's a simple application that we'll deal with a little bit later when we talk about rock fabrics. But it's